frequency analysis. And we will be studying how to plot the response of a transfer function when given a certain input function. So, for example, here we have a circuit represented by a network function. So to study the behavior of a network as a function of the frequency, we analyze the network function h j omega as a function of omega, or hs here, to simplify j omega ss. So we have, for example, if we have an input of a0 exponent j omega t plus theta, after entering this circuit represented by network function, then the output will be equal to a0 h, the magnitude, h j omega, exponent j omega plus theta, exponent j omega t plus theta. Okay. When we have b cosine omega t plus theta, basically the same here, only this is expressed in a complex Euler formula, while this one is expressed in a sinusoidal function. Then put into the transfer function hs, the output will become b0, the magnitude of h j omega, and then cosine omega t plus theta with additional phase angle hj omega. Okay. So the magnitude m omega represents the magnitude of the transfer function. The magnitude of the transfer function h j omega. The phase angle phi omega equals to the phase angle of the transfer function h j omega. Okay, so then the complete response, or the complete representation of the transfer function h j omega will be equals to the magnitude m omega multiplied to the phase with exponential notation, with the Euler notation, exponent j phi as a function of omega. Phi here is the phase. Plots of m omega and phi as omega as a function of omega are generally called as the magnitude and phase characteristics of the transfer function. And this is what we call as a Bode plot. And usually we express not linearly, but instead as logarithmic versus logarithmic. For the magnitude, it is expressed as 20 times the logarithm of 10 base logarithm of the magnitude as a function of the frequency, versus the log of the frequency, 10 base logarithm of the frequency, while the phase is expressed with the y-axis equals angle, the phase angle itself, versus the x-axis, the 10 base logarithm of the omega. So the unit is usually called as decibel. So what does decibel mean? It originated in the past as a measure of relative radio power. So the power of the second signal P2 in decibel over P1 is expressed as 10 logarithm of the ratio between power of the second signal divided with over the power of the first signal. And since power itself equals to I squared times R, it also equals to V squared divided by R. Then the P2 in decibel over P1 equals 10 log. If we express P2 as V squared as in voltage, this becomes 10 log V2 squared over V1 squared. Or in current, it becomes also 10 log I2 squared divided by I1 squared. And the square here becomes a multiplication factor to the coefficient in front of the logarithm. That is why the voltage ratio in the relative voltage in decibel becomes 20 log the voltage magnitude. current also 20 log of the magnitude of the current, and the gain also is 20 log, the 10 base logarithm of the gain. Okay. So using log scales, the frequency characteristic of network function have, by using the log scale, then the frequency characteristic will have simple asymptotic behavior. These asymptotes can be used as reasonable and efficient approximation of the actual characteristic response. Yeah. So we can use, of course, MATLAB or Octave, other computing software to graph the plot, but we can also first, by using the log, we can estimate how will it look like, the graph, the characteristic function, how would the characteristic function look like, yeah, as the magnitude as well as the phase. For example, here, if we have a general form of network function, yeah, showing this basic terms, we express h j omega, the transfer function of a network, equals to k0 j omega plus minus n multiplied to 1 plus j omega tau 1 multiplied by 1 plus 2 zeta 3 j omega tau 3 plus j omega tau 3 squared, etc., divided by 1 plus j omega tau a multiplied to 1 plus 2 zeta b j omega tau b plus j omega tau b squared. Okay, this one is the k0 factor is the frequency independent, so it is a constant, a multiplication constant that doesn't vary with frequency. And we have the full zero at the origin, yeah, j omega at the origin at the 0 plus power plus minus n. Then the first order term, we have the first order term, 1 plus j omega tau 1 at the upper part is the 0, the lower part is the pole. And we have the second order term here, yeah, with the zeta 3 here and tau. The quadratic term for complex conjugates, poles, and zeros. Okay. Then we express h omega as 20 log h omega. Yeah, we express it in decibel. Then, as we know from logarithmic law, logarithm AB equals to logarithm A plus logarithm B. Okay, and logarithm n over d equals to logarithm n minus logarithm d. So this we use to estimate how the graph will look like of this transfer function. So then from this, it is equals to 20 log k0 plus plus minus this n, this is this exponent, become a multiplication factor, n times 20 log j omega, magnitude of j omega, plus, yeah, because it's multiplication, 20 log magnitude of 1 plus j omega tau 1, plus 20 log the magnitude of this, yeah, the quadratic term, 1 plus 2 zeta 3 times j omega tau 3 plus j omega tau 3 squared, plus etc., yeah, the other terms. And for the denominator, then we put negative here, negative 20 log 1 plus j omega tau a, negative 20 log 1 plus 2 zeta b j omega tau b plus j omega tau b squared. Okay, the phase angle, to estimate the phase angle, when we have multiplication, the phase angle will be addition of the phase angle of the first factor and with the first phase angle of the second factor. Yeah. Phase angle of z1, z2 equals to phase angle z1 plus phase angle z2. Phase angle z1 over z2 equals to phase angle z1 minus phase angle z2. So from here, then the phase angle of this h j omega equals to 0. Yeah, since k0, this is frequency independent, it doesn't have any phase. J omega is 90 degree, yeah, 90 degree, but then there is a plus minus power here. So it is n times this 90 degree, plus minus depending on the polarity of this power, yeah, either it is positive or negative. Plus then the phase angle of this part is arctangen of omega tau 1 divided by 1. Omega tau 1 divided by 1. Then the arctangen of this part, which is arctangen of 2 zeta 3 omega tau 3, yeah, divided by 1 minus, so this become j square will be equal to negative omega tau 3 square, yeah, divided by 1 minus omega tau 3 square. So this is the real part, this is the imaginary part of this term. Negative, then the phase angle of the denominator part. You get here arctangen of omega tau A divided by 1, negative arctangen of 2 zeta B omega tau B divided by 1 minus omega tau B square. So display each basic term, this term separately, and after that we add each result, yeah, by this operation, adding or subtraction, to find the overall or the final transfer characteristic. Okay. So if for the constant term, yeah, the first part here it is a constant, so it is drawn as this 20 log k0, yeah, the magnitude characteristic. The phase characteristic here for the constant is 0 degrees, so just 0 degree, yeah, the phase. Here the right y-axis represent the phase angle, the left y-axis represent the log of the magnitude k. The x-axis represents the omega, the frequency in radian. Then for pole 0 at the origin, okay, j omega equals to 0 plus minus n. Yeah. Then the magnitude j omega plus minus n in decibel equals to plus minus n times 20 log omega. Okay. Yeah, while the phase is a multiplication, plus minus n multiplied by 90 degree, yeah, because every increase of j omega, it increases the phase by 90 degree. The x-axis log is log 10 of omega, yeah, like 10 base logarithm of the omega or frequency. So this, yeah, n plus minus n times 20 log omega. Log omega here, then this will be this as a function of omega. This becomes a straight line. So if it is positive, yeah, then it increases with a positive slope, but if it is negative, it is decreases with a negative slope. Here we see it will, when dealing with pole or 0 at the origin, the magnitude characteristic decrease with a slope of minus 20 times n decibel per decade. Per decade means every multiplication of 10 of the frequency. Yeah, because every multiplication log 10 is 1, right? So log 10 is 1, so the decrease or increase, the slope will be 20 times n over 1 decade. The phase characteristic, on the other hand, will remain constant. It's not a function of frequency. The magnitude is a function of this power n. N plus minus n times 90 degrees. So this is if minus n. If it is plus n, like this, if it is plus n, then the magnitude increases as a function of frequency with a slope of 20 times n per decade. Okay. Now, with the simple pole or 0 of 1 plus j omega tau, the first degree, the first degree pole or 0, 1 plus j omega tau decibel equals to 20 log, yeah, square root of, so this is shown in this one, yeah, 20 log multiplied by 20 log of 1 plus j omega tau 1 plus j omega tau. Okay. Then this will be equal to 20 log square root of, because this is a real number, a complex number, real with imaginary number. So the magnitude will be square root of 1 plus omega tau squared. The phase angle will be arctangen of omega tau, right? Omega tau divided by 1. So if this is the magnitude, if omega tau is much less, if the value is much less than 1, okay, the square root of 1 will be equals to 1, right? Log 1 equals to 0. Okay, so then the 0 will be the low frequency asymptote. When omega reaches 0, very small, or reaches 0 hertz, then the magnitude of the characteristic of the transfer function will be equals to 0. The phase angle, on the other hand, when this is approaching 0, it is also equals to 0 degree. When omega tau, however, is much larger than 1, in which case then very high, so it means then the magnitude of 1 plus j omega tau dB will be equals to 20 log 10 omega tau. So this is much larger than 1. 1 is negligible compared to omega tau. When omega tau is squared, then being root, and then the value will be 20 log omega tau, right? So this will become the high frequency asymptote at high frequency with a gradient of 20 decibel per decade. The phase angle will be 90 degrees, arctangen, because this is omega tau is very large, or approaching infinity, then the omega arctangen of infinity will be 90 degrees. So the two asymptotes at 0 as well as 20 log omega tau will meet when omega tau equals to 1. 1 square is 1, 1 plus 1 is 2, square root of 2. So this is the corner break frequency. At the corner, so omega tau equals to 1, and the asymptote is 0 decibel. The curve is at 3 decibel. Distance to the asymptote is 3. Then when omega tau equals to 2, the asymptote will be 6 decibel and the curve will be 7 decibel. Let's see here. So for here, this is the simple pole, 1j omega tau. The magnitude is this, so in the left side. So this is the break, the corner or the break frequency, when omega tau equals to 1. This one, omega tau equals to 1. For example, here the first one is this part, this one. When omega tau is much larger than 1, here the slope is 20 log omega tau. So this is 20 log omega tau. Okay, so it's a linear function towards this log omega tau with a gradient of 20 decibel per decade. However, when below omega tau is much smaller than 1, this part, then it is approaching towards 0 decibel. And the phase angle is shown in this line. Okay, at the 0, it is at the omega tau equals to much less than 1. The phase angle is 0 degrees. When the phase angle is much larger than 1, the phase angle is 90 degrees. And at omega tau equals to 1, the phase angle is 45 degrees. 45 degrees. Then, so this is the high frequency asymptote. Yeah, so it will increase linearly as a function of the log scale here with a gradient of 20 decibel per decade. This is the low frequency asymptote, the blue part here. This is the asymptote for the phase. Yeah. This one is the asymptote for phase, 45 with increase of 45 degrees per decade. Okay, so this is with simple zero, and this is with simple pole. So if it is simple zero, it is in the upper part, right? So the magnitude here increases. While if it is in the lower part, in the denominator as pole, then the magnitude decreases here. This is the magnitude from 0 to then decreases at minus 20 decibel per decade. Yeah, and while the phase is from 0 and then decreases with minus 45 degrees per decade until reaching like minus 90 degree. While as 0 in the upper in the denominator part, the phase angle from 0 degree increases with 45 degrees per decade, reaches 90 degrees. Now, more difficult approximation for the quadratic pole or 0 T2, yeah, at 1 plus 2 zeta j omega tau plus j omega tau square equals to 1 plus 2 zeta j omega tau minus omega tau square. This one. Okay, so this is becomes minus. So the magnitude, yeah, will be 20 log this one, the square root of 1 minus omega tau square. The real part is 1 and this one, and minus omega tau square. So this becomes the square of the real part, 1 minus omega tau square being squared, plus the square of the imaginary part, this one, 2 zeta omega tau square, and the square root of that. So this becomes the magnitude of the quadratic pole or 0T2. Then the phase angle is the arctangen of the imaginary part divided by the real part. So arctangen of 2 zeta omega tau divided by 1 minus omega tau square. So from here, now, if omega tau is much less than 1, so this is can be approximated as 0, this is become just 1. So 1 square root of 1 is 1. Log of 1 equals to 0. So at omega tau is much smaller than 1, the value here, the magnitude is approximately 0. Then this is will become the low frequency asymptote. The phase angle, on the other hand, is 0 over 1, so also 0 degrees. Arctangen of 0 is 0 degree. When omega tau is much larger than 1, so this one will be negligible. So this equals to omega tau power 4. Yeah? Omega tau power 4 plus 2 zeta omega tau square. And this can be approximated as 20 log omega tau square. Yeah? So because this minus omega tau square plus 2 omega tau square. This is much larger than this one. Yeah? So this, you only take into consideration this term, which is equal to omega tau power 4. Omega tau power 4 being square rooted becomes omega tau square. So the high frequency asymptote will be 20 log omega tau square. Yeah, so this, the 2 power here becomes in logarithmic, becomes the multiplication factor to the front. So 2 times 20 becomes 40 log omega tau. So it is a linear function of the log omega tau. It is the x-axis, but the gradient is 2 times 20, 40 decibel per decade. Okay. The phase angle, on the other hand, so if omega tau much larger than 1, so this is negligible. So this is cancel each other, omega tau cancel. So 2 zeta divided by omega tau. Yeah? Since when omega tau is very large, so this become then negative infinity, negative or the phase angle is 180 degrees, ya, rectangle of 2 zeta omega tau. So this becomes, let's see, so this is negligible in this case, so arctangen 2 zeta omega tau divided by minus omega tau square. So this is cancelled, this is 1, so become arctangen of 2 zeta over minus omega tau. So this one, yeah, when it is very high, so this equals almost to omega is very high, the high, then equals to 0, yeah, and then it will, the 0, the arctangen will be 180 degrees. Then what if omega tau equals to 1? If this is equals to 1, so 1 minus 1 equals to 0. Okay, and this will be equals to omega 2z times 1, 2 zeta, 4 zeta square. So equal to 20 log 2 zeta. And 20 log 2 zeta, the magnitude of this. Yeah. Then the phase angle here, when omega tau equals to 1, 1 minus 1 equals to 0. Okay, so this is equals to infinity. Infinity, then the arctangen of infinity is 90 degrees. Okay, so when omega tau equals to 1, this will become the corner or the break frequency. Yeah, so at very small frequency, the low frequency asymptote is 0, while at high frequency, the asymptote is increasing with 40 decibel per decade. At the corner of the break frequency, it is this constant, 20 log 2 zeta. Omega tau here will be equals to then square root of 1 minus 2 zeta square from here. So when omega tau equals to the square root of 1 minus 2 zeta square, this is the damping ratio. Then the decibel, this one will be equals to 20 log 2 zeta square root of 1 minus zeta square. And the phase angle will be arctangen of square root of 1 minus 2 zeta square, yeah, because now the omega tau is replaced by this. So this equals to my 2 zeta, yeah, 2 zeta, 1 minus 2 zeta square divided by zeta. And let's do this first. Okay, so this is for zeta less than square root half of square root 2. So this is the resonance frequency of the quadratic pole or 0. So if we draw this, this is the graph will vary depending also on the value of zeta, yeah, the damping frequency. If zeta is 1, so this is, it will be like this. This the lowest curve. Okay, the low frequency asymptote is 0. The high frequency asymptote, when it is much more than 1, omega tau much more than 1, decreases, yeah, with, so this is for pole, yeah, for pole. Pole means the denominator, that's why it's decreasing with a slope of 40 decibel per decade. Then at omega tau equals to 1, this is the value, the corner or break frequency. This is 20 log 2 zeta. Zeta is 1 here, then 20 log 2, logarithmic of 2 is about minus 3 decibel. So this is about minus 6 decibel. When the zeta here decreases, yes, it decreases, then you have a value of, this becomes the point here, the corner of break increases as well. Yeah, like this, when zeta equals to 0.1, so this is equal to 0.2, 2 to the power of minus 1. So this become negative yeah, this value increasing since this is pole, so it's the reverse, so it increases upward. And when zeta equals to 0, there is no log 0, 10 to the power of 0. This is then infinity. So here we don't have any value for the corner or break frequency here when zeta equals to 0. Okay. Then this is the phase for the quadratic pole. Yeah, as you can see here, the slope, the phase at the very small frequency is 0, at very high frequency is 180 degree. Yeah, since this is pole, the denominator part, that's why it is minus 180 degree. At the corner or break frequency, it is minus 90 degrees here. Okay, then at the other part, the phase is like this. And omega tau equals to minus square root of minus 1 minus 2 zeta squared. So these graphs are inverted for a 0. So when we analyze for 0, which means 0 means the denominator part of the transfer function. So instead, it will be here like this. Should use different ink color like this, this, and also like this. Something like this. Okay, the inverse part. Let's get some example here to plot the transfer characteristic for the magnitude and the phase. Voltage gain is given here, dV as a function of j omega equals to 10 to the 10 times 0.1 j omega plus 1 divided by j omega plus 1 times 0.02 j omega plus 1. So here we learn the 0, yeah, the constant characteristic is this one, 10. So this becomes 20 log 10 later as the constant magnitude. This is the first 0, yeah, normal 0. And then the pole has 2, a simple pole, at minus 1 as well as at minus 1 over 0.02. So draw the asymptotes for each of the term. So here, from here, the break or the corner will be here at 1 hertz, at 1. At this one from here, this is at 10. This is 0.1 plus 10 equals 1. Then at here is at 50. Okay, at 50. So then we draw it here. This becomes the constant magnitude. 20 log 10. Log 10 is 1. So this becomes 20 decibel from this contribution from the first term here. Okay, the phase angle is constant at 0 degrees. Yeah, at 0 degrees. No, not a function of frequency. Then from the first pole, j omega plus 1. Okay, the low frequency where asymptote is 0, then after j omega equals to 1, the break order at 1, then it will decrease, yeah, with slope of minus 20 decibel, yeah, minus 20 decibel per decade. So per decade here, we say after 1 hertz, after 1, not 1 hertz, but 1 radian per second, become 10 radian per second, it decreases by 20 decibel. Further to 100, it decreases by 20 decibel. Yeah, minus 20 decibel per decade. The slope, the phase, yeah, at 0 becomes minus 90 degrees at frequency of 10. It decreases by minus 45 degrees per decade. Okay, so at then much larger than 10, it becomes minus 90 degrees. Then for the first zero, yeah, the corner of break frequency is 10 radian per second. Okay, so before 10 radian per second, the asymptote is at 0 decibel. Then after 10 radian per second, it will increase with a gradient of 20 decibel per decade. Then the second, the phase also is at 0. Then after it increases by 45 degrees per decade. Then the last one is the second pole, yeah, whose corner break frequency is 50 hertz. It is at 50 hertz here. Okay, this is the corner of break frequency for this pole. So before 50 hertz, the asymptote is at 0 decibel. After that, it decreases by minus 20 decibel per decade. So the phase is like this. So now the overall transfer characteristic will be composite of all this drawing. Okay, so we draw here this 20. So this is the composite. Yeah, at between 0 to 1 radian per second, the composite will be 20 decibel. Between 1 and 10 radian per second, the composite will be is 0 plus this plus this. So decreases from 20 decibel to 0 decibel. So from 10 until 50 radian per second is the composite of this plus this plus this plus this. Okay, so this plus this 20 decreases like this, but then it increases by this 20 decibel per second. So then it will just flat at this 0 decibel. After 50 radian per second, it will decrease further, yeah, the addition of this plus this is this 20 decibel, this, and minus 20 decibel per decade, and this is also minus 20 decibel per decade. So this will decrease in this direction. The phase is similar. We add the response from each of the pole and zeros like this. So at this between 0.1 to 1 radian per second, the composite phase will decrease by minus 45 degrees per decade. Between 1 radian per second to 10 radian per second, yeah, this plus this plus this, it is just flat, yeah, because this is 45 degrees per decade. This is minus 45 degrees per decade, it just become flat. And then plus this one, 0 degrees. And this branches at this 5, like this, branching downward. After that, becoming flat again, then downward again, then flat again. Okay. So yeah, this is the composite magnitude like this. If we draw using MATLAB or Octave, it will look something like this. And the composite phase is like this. Okay. Now, example again, second example, generate magnitude and phase plots for this gain voltage j omega with a function 20 times j omega plus 1 divided by j omega square times 0.1 j omega plus 1. So the corner of break frequency will be 1 radian per second here at 0 pole, right? This one will be at 10. Okay, 1 and 10, 1 and 10, as well as 0. Draw the asymptotes for each of this. Okay, then the first one, 25, the constant, it will provide 25, a constant of 25 log 25. Okay, so it becomes 20 log 25 decibel. Yeah, 20 log 25 equals to about 2 something, yeah. So 20 log, it becomes then 28 decibel. The phase is 0 degrees. Yeah. Then the first 0, the break corner is 1 radian per second. So the asymptote before 1 radian per second is at 0, at low frequency asymptote. Okay. Then at high frequency asymptote will be 20 log J omega. Yeah. Then increasing by 20 decibel per decade. Yeah. Okay. Then the phase frequency will increase, yeah, from 0 degrees until 90 degrees with an increase rate of 45 degrees per decade. Okay, then the asymptote will be 90 degrees after omega equals to 10 radian per second. The third pole, yeah, here is j omega squared. So this is at 0 pole. So from the beginning, and the power is 2 here, so 40 log omega, the magnitude, yeah, 40. Since this is pole, so this is, the gradient is negative because it decreases by 40 decibel per decade. So from 0.1 to 1 here, decrease by 40 to 0, from 0 to negative 40 decibel at omega equal 10. The phase angle here will be minus 180 degrees. Then the second pole is at 10 radian per second. So before 10, the asymptote is at 0 decibel. After then it has a corner break frequency here. Then after that, it will decrease by 20 decibel per decade. Yeah. Now with the phase angle decreases by minus 45 degrees per decade. Now we form the composite. Okay. So then at this part, yeah, it will be the addition of 28 plus 40 or 68 here. This is not drawn here. So at 1, it becomes 28 decibel, exactly at 28 decibel, because this other contribution is 0 here. Then between 1 to 10 radian per second, so this is minus 40, so this will decrease, yeah, this will decrease at minus 20 decibel per decade, because this increases by 20 decibel per decade, while this one decreases by minus 40 decibel per decrease. So as a result, it will decrease by minus 20 decibel per decade. And afterwards, it is the contribution for this will cancel the contribution of this, yeah. Then it will just decrease downward at minus 40 decibel per decade. And the composite phase, we can calculate similarly. So this becomes 45 degree increase from this minus 180 degree. So this at this stage, then contribution from this will cancel with contribution from here. So it will just be flattened. After that, it will decrease again with this minus 45 degrees per decade. So this is, if we draw the composite phase like this, while the composite magnitude is like this. So initially, here it decreases by minus 40 decibel per decade. Then having a corner frequency here at 1 radian per second, decreases by 20 decibel per decade. After that, at 10 radian per second, decrease again. Another corner or break frequency decrease then by minus 40 decibel per decade. Okay. And this is the value at 5 radian per second, k0 over j omega square, where it equals to 0 decibel. Yeah, from here equals to 0 decibel. The omega is equal to the k0 square root of k0. Okay. Let's draw now the sketch the magnitude characteristic of this transfer function g j omega with 10 to the power of 4 j omega plus 2 divided by j omega plus 10 divided by j omega plus 100. So the corner of break frequency is 2 radian per second, 10 radian per second, and 100. Yeah, 2, 10, and 100. However, the function is not in the standard form. So we have to put it to the standard form. So the standard form is into 1. Yeah? So because in the previous one, we always put the plus here 1. So and then it becomes a factor here multiplied to the j omega. Okay, so this becomes, if it is divided by 1, this becomes j omega 0.5 j omega over 2. This becomes j omega over 10 plus 1. This becomes j omega divided by 100 plus 1. We need to show about 4 decades because this one until 100. So if we draw here contribution from after, yeah, why it becomes 20? Because it is divided by from 10,000 divided by 2, then divided by 10, then divided by 100. So it becomes 10, 100, it becomes 20 here. Then first contribution from this will become 20 log 20 log 20 is about 25 decibel. Okay, log 20 means about 2.5. 0.125 times 20, 1.25 times 20 becomes 25 decibel. The phase is 0 degrees. The first 0 having a pole having a 0 of 2, having a 0 of 2, so 2 at 2 radian per second here. So then the second break corner frequency is at 10. And so here before 0 it is 0 asymptotic, then after that increases by 20 decibel per decade, yeah, from 2 radian per second until 12 radian per second. Okay, increases by, this is 12, yeah, and increases by 20 decibel per decade. Then the phase increases from 0 degrees to 45 degrees per decade until 90 degrees per decade, until 90 degrees, yeah, asymptotic, 90 degrees. Then contribution from the next pole here, which is at 10. So before 10 radian per second, it is 0 decibel. After that, it decreases by minus 20 decibel per decade. This while the phase angle decreases from 0 degree at minus 45 degrees per decade until minus 90 degrees. Asymptote. Then the third pole at 100 radian per second. Here, 100 radian per second. So before 100 radian per second, it is 0 decibel. After that, it decreases also by minus 20 decibel per decade. Then we draw the asymptote between 1 and 2 radian per second. So the asymptote of the decibel, the composite of the decibel will be this 125 plus 0, which is here, 25 decibel. Then after 2 radian per second, it increases, yeah, because of this increasing component by 20 decibel per decade until 12 radian per second. After which this compensate with this one become 0. Yeah, this one, and then yeah, this is just flat. Yeah, this is flat. After that, it decreases by minus 20 decibel per decade. Okay. Phase angle similarly, we can do similar addition composite, and then from there we can draw the composite phase. Okay, this is another example actually. Okay, let's have a break first. Then we continue with the next example. Let's have a break.